Ever wondered how AI can still make sense of data when it's full of noise, like trying to hear a friend's voice in a crowded room? Let's dive into a fascinating math-driven approach that helps machines handle this chaos. Here's the trick. Researchers use something called variance-preserving noise, a way to add randomness to data without wiping out its core patterns. Think of it like shaking a jar of marbles. The marbles' data points jumble around, but their colors and sizes, underlying structure, stay the same. Now imagine two noisy versions of the same data. One starts with a random seed, eta I, the other with a different seed, eta j. By comparing how these noises differ, the model learns to separate the true signal from the static. It's like figuring out what's real by watching how the noise shifts, kind of like spotting a hidden message in a static-filled TV channel. The math behind this, it's all about measuring how much these noises vary from each other. The result, a formula that shows how noise affects the model's ability to learn. It's like a roadmap for AI to adjust its strategy, whether to zoom in on details or step back to see the bigger picture. Why does this matter? It's the foundation for building smarter systems that thrive in uncertainty, from decoding messy biological data to creating flawless 3D models. Next time you see AI working its magic, remember, it's not just brute force. It's learning to dance with the noise. Ever wonder how scientists decode the invisible chaos inside a living cell? It's like trying to follow a symphony where every instrument is a gene, and the music changes second by second. But what if we could build a model that adapts to the noise, the chaos, and still hears the melody? That's exactly what this research is about. Traditional models treat data like a fixed map, static connections between points. But life isn't static. It's messy, dynamic, and full of surprises. So scientists designed a graph neural network, a system that sees data as a web of interconnected nodes, like a social network where each person, node, shares information with their friends' edges. But here's the twist. This network isn't stuck in one configuration. It's a dynamic social network that evolves in real time. Imagine you're at a party, and the guests, nodes, keep reorganizing into new groups, clusters, depending on the noise level. If the music is loud, high noise, they form teams to shout over the chaos. If it's quiet, low noise, they spread out to chat in detail. This is adaptive scheduling. The model adjusts how nodes connect, optimizing efficiency like a crowd navigating a busy room. How does this work in practice? Let's break it down. The model starts by taking input data, say 3D shapes or gene activity in a tissue. It creates two types of nodes, original ones like individual cells and coarse-grained ones, averages of clusters, like groups of cells working together. Then it uses KNN, a method that connects each node to its nearest neighbors, like forming friendships based on proximity. But here's the magic. As noise levels change, these connections shift, like a group of people rearranging themselves to stay connected despite the chaos. The real action happens during message passing. Think of it as a relay race. Data zips from detailed nodes to clustered groups, then back again. Specialized layers, GCNConv and GATConv, act like different strategies for passing the baton, ensuring information flows smoothly even as the network reshapes. This adaptability is key. Traditional models stick to fixed rules, but this one zooms in and out, like a camera adjusting focus, to handle both blurry and sharp data. To test this, researchers used two wild datasets. First, 3D shapes from Model Net 40, like teaching a model to recognize a chair by analyzing its parts. Then spatiotemporal data from biological systems, where both spatial and temporal dynamics matter. The results? The model outperformed static approaches, proving that adaptability isn't just theoretical, it's a game changer. So next time you encounter AI solving complex problems, remember, it's not just about processing data. It's about understanding the dance between signal and noise, structure and chaos. And that's where the real innovation happens. Thanks for watching, stay curious, and let's keep unraveling the science behind the tech.